Next up, we have Rakesh Reddy Kandula, who will be presenting Demystifying the Quantum Threat for Network Operators. Rakesh is a technical marketing engineer at Cisco and traveled all the way from Hyderabad in India to join us today. This is his second NANOG presentation. His first talk was building trustworthy network infrastructure at NANOG 89 in San Diego last year. Welcome back to Rakesh. It's a pleasure to have you again.
Thank you.
Well, and there's the light to give you the warning light.
Yeah, got it. Thank you. Hello, everyone. Good morning. Before I get started, except Chris, how many of you here are already into some sort of quantum security, quantum networking, or evaluating the threats? A quick show of hands. 2, 3. Okay. Good. So when I was a bit of background on why I have come up with this topic today, the context is, as a technical marketing engineer, I handle security for all our service provider routing platforms. So I primarily deal with building trustworthy systems, runtime security, secure boot, DDoS solutions, and now quantum security too. And when I looked at the number of queries that I got from our customers in the last 2 years versus the last 2 months, there's a huge spike. And why? In August is where we got those 3 candidate PQC algorithms finalized by NIST. And now I see the number of queries increasing. Another change is, earlier, all those questions were primarily from our customers dealing with military, federal, huge financial or banking customers, and research networks too. And that's changed in the last 2 months. I see a lot of telecom operators reaching out, large enterprises, and even some big web players reaching out, asking, hey, Cisco, what are your post-quantum plans? Should we be worried about all of this, right? So that's where I felt this is the right time to increase awareness around this whole quantum threat, look at this whole problem holistically, and make sure we don't panic, right? So that's the background behind why I have come up with this. Now, Chris has already set a right stage talking about the quantum threat in the context of transport security. What I would like to do is to take a step back and look at that single network device, either a router or a switch or a firewall, and look at what are the various layers within that single device that could be threatened by a quantum computer, right? And then we'll take the network level view, that what Chris was talking about, and look at what are the threats for transport security. So we'll do a quick walkthrough of the basic threat to cryptography. We have gone through that already, so I'll not spend much time on it. Then the core of the session is to look at those various areas of impact once you have a quantum computer available. And what are the solutions today? Like, what should we as network vendors do? What should you all as operators do? Can we wait for some more time? Or what cannot wait, right? So that's the agenda for my session today. So let's get into the details. As you see here, some of these quotes from history might seem funny now, but at that point of time in history, when each of these were like some new technologies coming in, there are always questions or doubts till something matures, right? I would say the whole quantum computers is kind of in a similar situation. So I'm not going to be arguing or debating about when would a quantum computer be available for us all. Our focus would be assuming that few years from now, we are going to have one. What's the impact from a network security point of view? And that's going to be the primary focus here. Another important point, as security professionals, we cannot sit and wait for an attacker to take advantage of the network and launch an attack, right? So we need to be a bit proactive. So let's take a look at what is that. Now, we all understand with quantum computers, there's a lot of good research that could happen. You could run complex simulations, medical research, all of that is good. But if that same quantum computer falls into the hands of bad actors, it could threaten the cryptography. And that's the problem, right? So we all heard from Chris that yes, the symmetric crypto is not going to be broken. It is quantum safe. So we are fine. So what's the problem? The problem is asymmetric cryptography, and that could potentially be compromised. So I'll spend a couple of minutes talking about that, and then we will look at the various areas of impact. Now, this is the crux of the basic fundamental principle when it comes to asymmetric crypto, right? You have a public-private key pair. Of course, these are some large prime numbers that are related to each other, where anything that you encrypt with the public key could be decrypted only with the corresponding private key, or vice versa. So there is a strong relation between the public and the private key pair. And this entire asymmetric crypto system has been working well for the last 40, 50 years based on two important assumptions. The first one being that private key is assumed to be safe and not revealed to anyone. So typically you use these hardware security modules, the HSMs or other stronger hardware protections to make sure your private key is not stolen. And your public key is something, as the name suggests, you would share it with everyone publicly. And what's the core concept? Let's say I have to prove I am Rakesh and I want to send a package to you, I mean a digital package. I would sign with my private key. So that is what forms your digital signature. And then when you receive the entity, you would use my public key, validate that signature, and then you know that yes, Rakesh has actually signed this, so I can trust the source, and then I can actually use the data that I sent, right? So this is the basic concept behind digital signatures, sharing identity, proving identity, or even in case of key negotiation, it's just the key that you use to encrypt differs, but the concept is the same, right? So this has worked very well so far based on another second assumption, which is key for today's discussion, right? The second assumption was that given your public key, with any existing classical computers today, even if you run the latest and greatest algorithms, deriving its corresponding private key is probably going to take 10 or maybe 15 years, right? So that is reasonably safe, and that's how our entire public key infrastructure today is working, right? It's deemed to be safe because your private key is well protected in your environment, and your private key cannot be derived even if I feed that public key to my supercomputers or something, right? Now that's going to change. So with quantum computers, that second assumption, right, that given a public key you cannot derive private key is no longer going to hold good. It might just take a few hours or maybe days to derive that private key. So remember, 10 to 15 years to few hours, and that is the threat. And as Chris mentioned, it's not any quantum computer that could do this. You need to have something called CRQC, cryptographically relevant quantum computer, to do this. So we still have some time, right? Few more years at least. Then what's the rush? Why should we all worry about now if I don't have a CRQC that could be used by a bad actor? So let's understand that. So when we look at the various areas of impact for network operators, vendors, or anyone, I would put this into three different buckets. The first one is in the context of software integrity, trusting the source of your software. So let's forget about network devices, routers. Even your laptops or the mobile devices that you have, how do you trust the source of the operating system on that? How do you know it's actually Apple that signed that software running on your Apple phone? How do you know it's Microsoft that actually signed the operating system running on your laptop? So wherever there is asymmetric crypto, wherever there is some sort of signing involved, that could be potentially compromised. Then the second aspect is the boot process. The moment you power on your device, how can you trust that your device went through a secure boot process? That needs to be quantum safe as well. And typically, if you look at a network device, it sits in a network for at least 10 to 15 years, right? So how do you make sure all your runtime and operational security features are also quantum safe, right? So you need to have a mechanism to trust your software or firmware. You need to trust your boot process and maintain the trust level for the entire lifetime of your device. So that's the first. We'll talk about that in the next few slides. The second aspect is identity. Now, whenever we talk about identity and certificates, we all understand it very well about individual certificates or server certificates issued by your certificate authority. But in the context of telecom networks, there is another important identity called device identity or hardware identity. Now, given the nature of deployments for service providers, your routers might be sitting in some remote, untrusted locations. You cannot always guarantee the physical security that typically your data centers or enterprises have, right? So, given that kind of a threat model for telecom operators, we need to look at having a quantum safe hardware integrity aspect as well. So I'll spend a couple of minutes explaining the concept of hardware integrity, the need for hardware identity, and we'll look at the quantum threat. The third one is what Chris explained very well in the previous session, impact to the transport security, right? If you have to now extend this whole thing to a network, and you want two different routers to talk to each other securely, how do you make sure that MACsec or that IPsec session is quantum safe? So let's look at each of these areas and understand what's the threat, what can we do now, and what are the standards saying for each of these areas. Now, here is I know most of you must be well aware of this workflow of how software signing works. So let's say if I'm a vendor, let's say I'm Cisco, and I need to publish a software image, a new release. I would build my image in my environment. I'll compute the hash of it. I'll sign it with my Cisco's private key, and then I'll package it and I'll say, hey, this is the software. I have signed it with my key, and you can use it. As customers, you would first use Cisco's public key, verify that signature, ensure that it's matching. Then you can trust that, okay, this software was actually published by Cisco. I can trust it, and then you install, right? Simple workflow, nothing fancy here. But what's the quantum threat? The first threat is on the hashing itself. I said, I'm going to sign that hash with my private key. So how do you make sure that hashing mechanism is quantum safe? So we have Grover's algorithm that says the effort taken for a quantum computer to compute the pre-image hash gets reduced by half or even 1/3. So we need to make sure the hashing mechanisms, the strength of the hash is sufficient to be quantum safe. Then the second aspect, the signing, right? There is a public private key pair, asymmetric crypto, and as we already know by now, it's not quantum safe. So that's the first problem we need to look at. Then the second one, the boot process. Okay, so we have a problem in trusting that firmware or software itself. Now, how do I trust my entire boot process? So as you see here, this is a common secure boot workflow where each stage of your boot process has an independent entity. Each entity has its own signature, its own hash, which means even if one of the stages of this boot process is compromised, the signature or the hash, that means you have a problem. You can no longer trust the state of the device because you can no longer trust the boot process. On top of it, a lot of vendors, like at least at Cisco, we adopt something called hardware anchor-based secure boot. What that means is, the moment you power up your CPU, even before we take it out of reset, there is an additional security chip, which is what we call as hardware anchor. It does some additional validations before we actually start the boot process. So we'll talk about it when I bring up the point about hardware integrity. But if you are using a vendor equipment that also uses such hardware anchors, that must also be quantum safe, right? Then comes the runtime aspect. So I have taken one example, which is a Linux concept, integrity measurement architecture. At the crux of it, it's simple. Once you have powered up your router, during the runtime, how do you still trust the files that are getting executed? So what IMA does at the kernel level is, if you have to, let's say, run a BGP process, before I can trust the binary, the file on the router, the kernel does something called a measurement or appraisal. So essentially, it computes the hash of that file, and during the build process, let's say at Cisco, we also append the expected hash value and we sign it with a corresponding key called IMA key. So during the runtime, the router is able to compute that hash, verify that IMA signature, then it knows that it can still trust that BGP file, and then it actually runs the BGP process. And what is the quantum threat here? Again, there is a hash, there is a signing involved. So wherever there is asymmetric crypto, wherever there is public-private key pairs, it's not quantum safe, right? So let's take a look at what's the path forward for these basic building blocks. First, I said for hashing, this is the relatively easier one to actually solve. With a quantum computer, a CRQC, the effort to get the pre-image hash is probably reduced by half or 1/3. So the recommendation is, if you need the same level of security that's provided by a 128-bit hash, we all must use either 384 or at least 512-bit hashing. So wherever there is a hashing involved today, let's start moving to 512, stronger the better. Then what about the signatures? This is where the recently approved NIST algorithms come into picture. Those candidate algorithms that have been approved, those could be used. Or even before these NIST algorithms came out, there is a whole area called hash-based signatures, right? These are proven to be quantum safe, and they have been around for probably 10, 15, or 20 years now. Now, depending on what module, what software or firmware that you are signing, you could pick which algorithm to use, right? So essentially, the hash-based signatures, they are also called as one-time signature pads. So if you're like signing a microcode or a BIOS module, you could use that. Or if you're signing your runtime operating system binary itself, you could use the recently approved algorithms, right? So that's the story around trusting the firmware or the software. So let's move on to the hardware identity problem. So I'll spend a few minutes explaining the need for a hardware identity at all, and then we'll look at the quantum threat. So if you look at typical service provider deployments, one of the biggest problems, the complaints that we hear from our customers is there is a lot of counterfeit or fake hardware out in the field. So for you to trust if this device that you are getting is a genuine Cisco device, how do you know? It's no longer sufficient if you just write a serial number in some flash memory, right? That's very easy for attackers to modify that. So we need cryptographic hardware identity. So that's the first reason why you would want to avoid the problem of counterfeit hardware. The second problem is resale market. So what if the gear that you're buying in the resale market, what if it has been tampered with? How can you trust that the CPU or the forwarding ASIC sitting on that device hasn't been tampered before it's resold to you? So for the reasons of counterfeit and tampering detection, you need some mechanism in the hardware to have some sort of identity. The second common problem or challenge, I would say, for service providers is scale. Typically, a telecom network spans an entire nation, or in some cases, across the globe, right? So how can you, at scale, onboard new devices into your network and do it in a secure fashion? So, which means before you can onboard the device, you should have a mechanism to trust the hardware, the software, and the provisioning mechanism itself. So this is where we have some standards like secure zero-touch provisioning, RFC 8572. That's an example. So a lot of our customers actually use that. So if you need to employ these kind of secure provisioning mechanisms, you again need some sort of hardware identity. Another reason, most of the cases, if you're a very large-scale operator, you use third-party services to deploy your devices in the field. Someone to go physically ship the device there, do the cabling, and power it up. What if that genuine device got swapped or got tampered before it was provisioned by that third-party vendor? So you need some remote way of validating the integrity of hardware. So these are some of the reasons why hardware identity becomes very critical for telecom deployments. So what are the requirements if you have to solve these problems? First, you need a cryptographic hardware identity. So we'll talk about that. Then you need to have a mechanism that can detect if that CPU or that forwarding ASIC have been tampered with. Then most of the times, some of these devices have these security chips that provide the entropy for your random number generation too. So we need to have a hardware source of entropy too. And as I said, remote attestation. What that means is when you deployed your device, you must be able to validate that cryptographic identity even remotely. It doesn't have to be a physical presence over there. So how do you solve this? So we have what are called as trusted platform modules, TPMs. These are the chips that you also find in your laptops as well. It's an industry standard term. TPMs or other security chips like that have some features that are helping us with this challenges. One, they have some sort of cryptographic identity. So that is solving the hardware identity problem. The secure boot problem, remember I said there are different stages of boot, and each stage of boot goes through a set of measurements. And these chips, these security chips, have something called PCRs, the platform configuration registers inside them. They record the boot measurements so that once your router is up and running, you can query these measurements and verify them with the expected values. So that's how you establish trust in your boot process. Or if you need some disk encryption or data at rest protection, these chips also offer some sort of on-chip storage as well. So these are some industry examples. Google supports this, OpenTitan. If you follow OCP project, Calyptra is another hardware root of trust. Apple used to use their T2 homegrown security chip. We at Cisco use what is called TAM chip, Trust Anchor Module. So no matter what security chip is being used or which vendor, end of the day, if your network device has these kind of additional security chips on it, those must be quantum safe as well. So let's look at what are the areas that could potentially be compromised when you're talking about hardware security. The first one, I said cryptographic identity is the key, right? So we have to make sure that identity that a vendor is programming at the factory, that must be quantum safe. Then most of these chips, in addition to that factory programmed identity, they also let you as operators onboard your own cryptographic identity as well. So as an end user, if you want to onboard your own identity to your routers, that must also be quantum safe. Then I said there are chips out there that help in detecting if the CPU or the forwarding ASIC have been tampered with. It could be a supply chain attack, or it could be a rogue internal employee, it doesn't matter. All those mechanisms that are helping with tamper detection, that needs to be quantum safe. And all those boot stage measurements I talked about that are recorded inside the chip, all those hashes, they must be quantum safe. And as I said before, a telecom network equipment sits in the field for 5 or 10 years. What if you have to upgrade the firmware of that security chip? That firmware signing and the methods to update that, it must also be quantum safe. So let's look at the solutions. What's the path? So this is a tough one, right? Because this is not a simple software upgrade. An entire industry has to change to support this. Now, the first block that you see here, which is in green, if this was the previous nanog, that would also be not in green because the NIST algorithms were still not finalized. Now that in August, we had those 3 candidate algorithms available, we reached that first milestone. But it's a long road, right? If you need any of this quantum safe hardware to be available, any of these chips to be available, Trusted Computing Group, TCG, that's the consortium that actually puts out standards for these TPM chips. So even if some of us have our own custom security chips, we stick to the TCG standards. So now TCG must come up with the new standards using those newly approved algorithms. Then the chip vendors, the ASIC vendors, they must start manufacturing those, and then comes the OS support, right? Then the new software must start using these hardware, newer algorithms and newer ciphers implemented in the hardware. So when we are talking about quantum safe hardware, what do we mean? So we have to look at the firmware signing itself, the identity part. I said for hashing, we should adopt at least 384 bits. Bigger the better, so probably 512-bit hashing for those PCRs. If not, minimum is 384-bit hashing. All those key enrollment mechanisms onto the chips, that must be quantum safe. And most importantly, all of this would mean your CPU vendors like your Intel, AMD, or your ASIC vendors, everyone has to move to this, right? So this is going to be at least a few more years of journey, but it's starting now, given that we have some of the algorithms available now. So this is for your offline consumption. I have put together those list of approved standards and other pre-existing post-quantum standards that were already there. These are in the context of software or firmware signing and the hardware identity that we discussed. Another one I would highly recommend you all to review offline is that CNSA, the Commercial National Security Algorithm Suite that NSA puts up. They have a good FAQ on the whole quantum computing aspect. So that's a good read to understand the entire landscape. Now, there is another aspect as well. All the features I talked about, all the security aspects, I would put them under a bucket called infrastructure security. What that means is, you're talking about a network device manufactured by a vendor and the boot process, which are like the core elements of any device, right? They are not optional, they are mandatory, and they are part of the device. But what about the software security features that you as customers, as operators, enable them based on your need? Simple example, SSH. That's the basic thing you need to connect to your device. The TLS, if you have a HTTPS connection or if you're enabling syslogs over TLS. So what's the story on the software support? So again, we are at the first step here. Those NIST approved algorithms are out. So the journey started. This part, I would say, is relatively easier when compared to that hardware support. So we have to wait for the OpenSSH and OpenSSL standards to come out that are incorporating those approved standards. Like there was an OpenSSH standard probably earlier this year, but that was still not the one that was part of the NIST approved algorithm. Then some of these need RFC updates as well. So there's a lot of IETF activity happening to make sure the RFCs are out using these new algorithms. Then comes we as network vendors to incorporate these new libraries, and then the operators to start upgrading your software. Now I understand the moment I say software upgrade, it's a nightmare for operators. So generally it's dreaded and you would want to do it only if you have some new feature provided in a new version, right? But when it comes to this quantum readiness, unfortunately, it's not a choice. Eventually, we all have to upgrade the software that supports the post-quantum algorithms. But it's a journey that's starting now. So this, I would say, at least by end of next year, calendar year 2025, you should have some sort of stable releases out there by most of the vendors, right? So because this is the software implementation. I would also like to point out to some other considerations. Given that these are all new algorithms, what's the status of certification? Some of you might be catering to federal customers as well, right? So you have FIPS certification. You need to go through common criteria certification. So that's another aspect to be considered when you need to upgrade to quantum safe software. Then the stability. These are all new standards, new software. So how do you make sure they are stable enough before you put it into your production networks? And the third one is interesting. You can't upgrade your entire fleet in a single shot, right? So it has to be gradual, which means at some point of your network, you need to run the classical algorithms, you need to have the PQC support, or if you have to interop with another vendor and they are still getting ready. So how do you design your software to make sure you can select the PQC mode or the existing classical mode? Should that be a global option or should that be at the application level option, right? So these are some of the considerations that network vendors must consider when they are building the software. Another aspect is, how do you test this? Okay, maybe there is a new OpenSSH library that supports this. Do we have an SSH client that supports these algorithms? Or if I want to establish a TLS connection, do I have a server that supports these, right? So there is a whole ecosystem out there that needs to start adopting the new standards. The last one, crypto agility, is a very important one, I would say, in this whole context. Even if you look at NIST or what NSA is saying, those algorithms that were announced in August, they are not the only algorithms. There is no guarantee they're going to hold out probably for the next few years or decades, right? They are very clearly saying these are quantum safe from what we know as of today. So there could always be changes to those. So this quantum transition is the right time for all the software designers and the network vendors to design your applications so that the crypto agility could be taken care, which means your software design must be able to incorporate any changes to these algorithms, any updates to these algorithms, rather than again waiting for 2 or 3 years to redesign your entire solution, right? So crypto agility is another important aspect to be considered in this whole transition of quantum security. Again, this is a quick reference for offline consumption, where all the aspects that I talked about here are listed, like what's recommended for image signing, what is recommended for firmware signing, key negotiation. And if you look at the first row, symmetric crypto is quantum safe, so it is still AES 256. We are not worried about that. For the rest of them, you have the list of algorithms here. Now let's switch gears. We were talking about a single network device so far and the different layers starting at the hardware, the boot and the runtime. Now what about the network level? When these devices have to talk to each other, this is where the impact to transport security comes in. I'll not spend too much time explaining the threat. Chris has done that already. If you just look at a high level, if you're establishing a MACsec or a IPsec session, there are two parts to it. The first part is the authentication or the key establishment phase, which means those two devices that need to establish a link have to somehow negotiate and come up with a common symmetric key, right? That is the second part. And that symmetric key, encryption is proven to be quantum safe, so we are not worried about that. What needs to be secured is that first part, that key negotiation part, because that relies on asymmetric crypto. And as I said before, the asymmetric crypto like RSA, Diffie-Hellman, ECC, they could be compromised by a quantum computer. But do we all have to worry about it now? Given that we don't have a quantum computer now, why care about it, right? Now, I would say not every customer out there, every network operator has to jump onto this right away. If you cater to a customer that's worried about forward secrecy for at least 5 or 10 years, like typical military financial institutions, yes, then you have to start looking at some of these aspects because of the harvest now and decrypt later threat. But if you are catering to small enterprises, or a simple example I see is like movie theater booking, right, service. We don't care if someone's going to break those transactions 5 years from now, right? But if you are a customer who is, you are an operator catering to a customer that's falling into that first bucket, we should look at taking some action starting now. So what are the solutions we have? We have been saying from the beginning that symmetric crypto is safe, right? So the common question you can ask is, why not use that in that first part of the key negotiation? Yes, that's nothing but the pre-shared key. This has been a standard, this is in the context of MACsec. It has been a IEEE standard for a long time, probably 20 years. The second medium-term option is the quantum key distribution, which is supported by a lot of network vendors out there. But the long term, there is no choice. We must all adopt the newly approved algorithms. That's the only option. However, if you, like I said before, if you have a customer who is worried about the quantum threat today, you could probably recommend the quantum key distribution or use the pre-shared key as well. So let's quickly walk through these three options and understand the pros and cons of each of them. This is simple. MACsec, if you look at bringing up a MACsec link, the pre-shared key is nothing but the network admin comes in and configures that same symmetric key on both the sides. And once you configure the same initial key, think of it as your initial seed, your actual symmetric keys for the data path encryption are derived based on that pre-shared key. I'm again simplifying this whole thing a lot, but end of the day, that data path key is derived from a common material that is configured by the network admin. So this is free of cost. This has been supported for a long time. Every vendor, network vendor out there supports. There is no interop challenges. However, if you have very stringent requirements on rotating your keys, or if you are worried about rogue internal network admins, because from security threats, it's not always external threat actors. Sometimes it could be rogue internal employees too. So if you are catering again to a customer that's worried about these, then pre-shared key is probably not an option. You need to move towards dynamic authentication. If not, I would say go ahead and use a pre-shared key option, zero cost, no software upgrade, it works. But as I said, if you need dynamic authentication, if you want to handle those rogue internal admin threats, we need to do something with that first part of that session bring up, right? So there are two options. One, you can have this new quantum key distribution hardware deployed in your network. Like if it's a military or a federal government that can afford the cost of it, they can do it. The source of the keys in that case is quantum source. And by the nature of the devices, they can detect if there is some sort of tapping happening on the links. So it's quite sophisticated devices. So they come at a cost, right? Or there are also network vendors that support a similar quantum key distribution methods, but in the software option. So no matter which one you would want to consider, I will just explain the core concept behind this, so that whether you're using a Cisco, Juniper, or Nokia, or doesn't matter, let's understand the concept of the key distribution and how the quantum key distribution is helping us. So if you look at the traditional key distribution method that happens today, again, this is in the context of MACsec. In the MACsec world, the data path encryption key is called SAK, the security association key. So let's say if these two routers have to establish a connection, the MKA process essentially helps with doing the dynamic authentication. You go through .1x authentication, and let's say the peer 1 is acting as a server and the final encryption key is derived. What happens next? It must communicate that with the peer device. And that is where the problem comes, because that derived symmetric key is encrypted with a asymmetric algorithm. And then you share it with the peer. And that's where the problem is. Our assumption for this discussion is there is always a bad actor out there sitting on the network that's tapping the flows. So in this case, that encrypted session key is also tapped. And once a quantum computer becomes a reality, they can decrypt that key negotiation phase, and they would know what was the data path key. So you don't have to break the symmetric key encryption. Once I know the key, I can straight away decrypt the flows, right? Then how is quantum key distribution solving this problem? So this is where it gets interesting. No matter the source of that quantum keys, whether it's a software, whether it's a hardware or something else, right? You still have to share the symmetric key that is going to be used with your peer. But in this case, you're not sending that encrypted session key. Rather, you're only sending some identifier or some metadata about the key. So if, let's say I derive the key, there is also a key number associated with it. And I'll say, hey, use key number 100. So even if there is an attacker sitting there, and if they can see that, okay, they are using key number 100, but what can they do with that key number, right? Because they don't know how to derive the key from that key number. On the other hand, the two communicating routers, they have access to their own respective QKD sources. So what they would do, give me the key corresponding to 100, and that's how these two end up with the same symmetric key, right? So even if you have an attacker sitting there, even if they are tapping your flows, you're still safe because you really did not exchange anything about the actual symmetric key there. I'm only sending some metadata, and it doesn't matter even if an attacker has that. So how does this look like in a real deployment, right? So as I'm showing here, each of the routers have access to that quantum key hardware there, or could be a software. And the peer 1 has derived the key and the key number 1. And if you see, it's only saying use key number 1, nothing about the key. Now the router 2, the peer 2, goes to its QKD source. It says, can you give me the key corresponding to key number 1? And that's it. And now both the routers have the same symmetric key, and they can start exchanging the data. They can encrypt with that common key. So the concept is very simple. It's just that the differences would be which vendor you're using, what's the QKD source, and all of that. Now, how does this look like? With an example of MaxSec, if you're using an external QKD hardware source, it's quite expensive, like I said, but your source of the keys is hardware. So if you're a defense or a federal institution where cost is not the problem, but additional security, this could be one option. As of today, these QKD devices have this distance limitation, but I hear there is active research happening to increase that distance that we could support. As of today, I think it's around 100 kilometers between two physical QKD hardware devices. And the cost aspect. So I would leave it to the operators to decide based on their end customers' use, whether to deploy a pre-shared key mechanism, or whether you want to have a hardware-based QKD or a software-based QKD. Then what about the long-term option? I said, right? There is no choice, but we must all adopt the new standards. So the right column here is what I'm showing about the PQC algorithms in the context of key negotiation, whether it's MaxSec or IPsec or TLS. So end of the day, every network vendor out there must start implementing the post-quantum crypto for sure. So what's the key message? My message out to all the operators is, please go back and first evaluate the various security features that you're currently using in your network. Look at which parts are deemed to be very sensitive, which parts are relatively okay, and then start preparing for your upgrades, or start pushing out your network vendors to incorporate some of these standards. One important aspect is, if you're planning for a hardware refresh in the next 2 or 3 years, I would say it's very critical now you include the hardware requirements in your RFPs or RFQs, because any new hardware that's going to be deployed in 2 or 3 years from now would probably be sitting out in the field for at least 10 more years. So we are much closer to the quantum threat. So if you are planning a hardware refresh, start looking at putting these requirements. Software aspect, evaluate what features apply to you, like SSH, TLS, and make sure you start planning your software upgrades accordingly. So that brings me to the end of my session. Thank you all for attending. I think we still have some time for questions. Thank you.
Thank you, Rakesh. That was very comprehensive and I think hopefully very useful for everyone. So we have 10 minutes left on the clock, but that does go into lunch. So do we have any questions? No questions?
Good.
Okay.
Hopefully it was useful. Thank you, everyone.
Okay. Thanks again, Rakesh. Thank you.
Thank you.